Chapter 8, Systems of Particles. Systems of particles covers the center of mass, Newton's second law for a system of particles, impulse linear momentum theorem, conservation of linear momentum, collisions, system with varying mass, a rocket. You can find them in a timeline. The center of mass. System. A collection of two or more bodies is called a system. And any force on the bodies inside the system from bodies outside the system is called an external force. The forces between two bodies inside the system is called an internal force. Sigma F internal force equal to 0 because forces appears in pairs. Action force and reaction force inside the body is always equal in magnitude and object interaction, but they never cancel out because they act on different bodies. Now we want to put all forces inside the system together. Definitely it will involve these two forces, and the sum of these two forces is 0. So of sigma F internal force is 0. A special point. Everybody has a special point called the center of mass. You look at this, a baseball bat. You throw the baseball bat, it turns around, but you look at a special point called the center of mass. It moves like a single particle, right? The center of mass of a body or a system of bodies is the point that moves as though all the mass were concentrated there and all external forces were applied there. Center of mass. We start with a system of a few particles, and then we consider a system of a great many particles. System of particles. Figure shows two particles of mass m1 and m2 separated by a distance d. We choose the x-axis overlapping with the line which connect the particles m1 and m2. x1 and x2 are their positions respectively. We define the position of the center of mass of this two particle system to be x center of mass equal to m1x1 plus m2x2 over m1 plus m2. Well, for the future, we will rewrite this one as sigma mi xi. This is sigma mi, okay? So in this case, we could extend to many points. Okay? And sigma mi is the total mass of this system. I'll replace it with m. Okay? In three-dimensional, we're similar. X column, Y column, Z column has similar formula. Okay. S column equal to sigma mi xi over big M. Y, we replace xm with Y column. Okay, this was yi, so it becomes Y column equals sigma mi yi m. I is the particle number I. Similar, Z column equal to sigma mi zi over m. What we do, we saw in a system, the number I, the particle number I, its location is Ri, Xii, Yij, and Zik, where I can be 1, 2, 3, 4, 5, up to many. And the center of mass, the location is R. It has three components. x, I, y, j, z, k. We based on above definition. We have x equal to sigma mi ri over sigma mi. And the sigma mi equal to the total mass of the system. So we have this one. And furthermore, if it is not separate masses, it's a solid body. We cannot separate one mass to another mass. So we change this mi as dm, very small mark, and the sigma becomes integration. So above equation becomes r equal to integration r mr divided by the m, where m is this total mass dm integration. And this we write in 3 components. We get com is this one, ri is this one. We find this one. We compare the ijk, the coefficient in front of the ijk. We get x equal to integration x dm of m. Y equal to integration y dm of m. Z equal to integration z dm over m, where m is the total mass equal to integration of dm. Now let me explain to you how I remember this formula. This is a basic formula. X equal to sigma mi xi over sigma mi. From this formula, we could extend to y z we can extend to integration dm and so on. How do I remember this formula? I just write equation. Sigma mi xi equal to sigma mi xi. I move this xi out. Or inside is 1, 2, 3, 4. Out, you don't have a sigma, so I change this one as a x You see that's x equal to sigma mi xi over sigma I. Exactly the same thing, all right? So, and then we extend to the integration, okay? Integration, this is equal to, this is the integration, m replaced by dm, x, and the sigma mi is big M, that's it. Now, important thing is, the position of the center of the mass of an object does not depend on the reference frame from which it is calculated. Okay? So you can find a good one, make things much easier. Okay? It's nothing to do with the frame. And this definition has been proved by experiments. Why this one? Has been proved by experiment. You can bypass one or more of these integrals. If an object has a point, a line, or a plane of symmetry, the center of mass such an object then lies at that point, on that line, or in that plane. For example, the center of mass of a homogeneous sphere, which has a point of symmetry, is the center of the sphere. The center of mass of a homogeneous cone, whose axis is a line of symmetry, lies on the axis of the cone. The center of mass of an object need not lie within the object. For example, you have a donut, okay, and the center mass doesn't have another dot. Yeah. Horseshoe, the center of mass of horseshoe does not have an eye, okay. If the object has uniform density rho or mass per unit volume, that is, its density rho is the same for all given element of the object as for the whole object, then we can write the density equal mass over volume. Okay, the small one is dm over dv. The big one whole as m over v. If it's a uniform, they are equal. Okay. Then we can write this one. by definition, x com equal to x dm integration over m. This dm is rho dv. This big M is rho v, okay? Where rho dv is the dm. Rho v is the big M. Also, same for the y com, the z com. Here we see rho in numerator, rho in denominator. They're the same, so we cancel out. Same thing for y and z. We can use this integration to find x com, y com, z com.
Is there a simple way to locate the center of mass of an irregular flat object? We'll hang the sheet from a support point near its edge. Since it is in stable equilibrium, we know that its center of mass is directly below the point of support. A plumb bob is hung from the same support point, and we snap the chalk-filled string to put a line on the sheet. Then we repeat the same action from another point of support. Since the center of mass must be located on both these lines, it must be at their intersection. If we suspend the sheet from the intersection point, it is stable in any orientation. This animation shows the forces acting on the sheet and the net restoring force that results when the center of mass is not below the point of support. We'll use this air table to demonstrate the motion of an object's center of mass. A flat piece of acrylic has been weighted on one side so that the center of mass is located beneath this orange spot. To show that the center of mass is located at the spot, we can balance it on a finger at that point. Now the acrylic is placed on the air table and given a push. The acrylic and the weight move in circles, but the center of mass moves in straight lines.
Sample. 3 particles of mass M1, 1.2 kilogram, M2, 2.5 kilogram, and M3, 3.4 kilogram, form an equilateral triangle of each length 140 cm. Where is the center of mass of these 3 particle system? Sample. 3 particles of mass M1, 1.2 kilogram, M2, 2.5 kilogram, and M3, 3.4 kilogram, form an equilateral triangle of each length 140 cm. Where is the center of mass of this 3 particle system? We run all the information. M1, mass 1.2 kilogram, X1 0, Y1 0, M2 2.5 kilogram, X2 140, Y2 0, X3 is the middle, so mass is 3.4 kilogram, X3 is half, 70. Y3 we can calculate from this triangle. 121. Then we put the formula. X com equals sigma M1 X1 plus M2 X2 plus M3 X3 divided by the total mass m1 plus m2, m3 equal to 33 cents. Y-com is equal to sigma m1 y1 plus m2 y2 plus m3 y3 divided by man. 3 put together, we get 3. So we get the answer. Total mass 7.1 kilogram. X-com is 83 cents here. Okay. Y-com 58. So this is the center mass of this triangle. Sample. Figure shows a uniform metal plate P, this is a P, of radius 2r, which a disk of radius r has been sampled out, removed in the example line. Using the xy coordinates system show, this is x, this is y, locate the center of mass com of this piece's plate. Now in this case we find if we put one piece here, okay, then we get this one. This one is just use the center mass is here, okay. Now this piece, look at above the x-axis and below the x-axis, they are symmetry. So you have a symmetry, we know the center mass must be located on x-axis. That means y p equals 0, com. How about the x? And we see, we took these two pieces as two particles. This particle mass, I know this one. The center mass is located minus r, right? Yeah. And this one, the location is what I want to find. So let's see this. We put it together. Where is the center mass? Here, 0, right? And by definition, this two pieces, it should be x1, m1, x1 plus m2, x2, divided by m1 plus m2. Here we call this one the small pieces. This is the p. This must be 0. Why? Because I take reference here. This is 0 at here point. Then we see numerator must be 0. I get ms xx plus mp xp equal to 0. Okay? So xp, the location where I want to find is minus mx ms of z. Let me write all these one. Ms is the mass, is the area, pi r squared, multiplied by a thickness t. This is the volume. Volume multiplied by density is mass. And MP is two pieces, big one minus smaller one. Big one is pi 2r squared. Small one is pi r squared. This is the area. We multiply by thickness t, this is the volume. And then multiply by the density, it is the mass. And this is 3 pi r squared t rho. And excess minus r. We put these 3 inside, we get xp. Xp about 1/3 I is here. The plot is a little bit wrong. It should be 1/3. Okay. Newton's second law for a system of particles. Newton's second law for a system of particles. Sigma f external equal ma com. F equal to ma, but each term have different meaning. 1. Sigma f external is the vector sum of all external forces that act on the system, not necessarily on the center mass, on the system, any particle. Forces exerted by one part of the system on another are called internal forces, and you must be careful not to include them when using above equation, because sigma f internal equal to 0. We have explained before. Second, m. M is the total mass of the system. we assume that no mass enter or leave the system as it moves, so that m remains the constant. This system is said to be closed. 3. A, is the acceleration of the center of mass of the system. This equation gives no information about the acceleration of any other point of the system, only center mass. Let's prove it. Well, R center mass equal to sigma mi over m, where m is the sigma mi. We write it down. We move m over here. M R equal to sigma m1 r1, m2 r2, m3 r2, and mn nn. Now, let me do something operation. We do the derivative with respect to time t on both sides. And m is constant, m1, m2 are constant. We take it out. So this formula becomes big M v dr dt equal to v. This becomes v1, v2, v3, vn. And furthermore, we do the derivative with respect to time t on both sides in this equation. We take this out, dv dt is acceleration. So this is a m1 a1, m2 a2, m3 a2, mn an. What is this? This is a sigma f acting on m1, and this sigma f including two parts, external force, internal force. We put this force together. All these forces including internal force and external force, and we summarize sigma f external force plus sigma f internal force. As we know, explained it before, sigma f internal force of a system is equal to 0. So we get f external sigma equal to ma dot. This is the Newton's second law for a system of particles. In the application of Newton's second law, the system of the particle may be replaced by a single particle located at the center of mass. The mass of this single equivalent particle being the total mass of the system of the particle. Okay. We rewrite this in 3 components. We get they are independent with each other as before. Okay. Sigma f x equal to m a x. Sigma net y equal to m a y. Sigma net z equal to m a z. They are independent. So this looks like a single particle's Newton's second law. And this single part is center mass. As we mentioned before, the center mass of a body or a system of bodies is the point that moves as though all the mass will concentrate there and all external force will apply there. 2 O's.
When we place a cylinder on this pair of inclined rails, it rolls down the incline. If we place this double cone on the incline, it rolls up the incline. Why does this object appear to defy gravity? The rails spread apart in the uphill direction. This and the shape of the double cone allows the center of mass of the cone to go lower as it moves up the rails. Here's a shot from the side. When we place this disk on an incline, it rolls downhill. If we place the same disk on the incline again, it rolls uphill. What could account for this unusual behavior? If we turn the disk around, the reason becomes clear. A heavy weight has been added to the disk near its edge, shifting the center of mass. The center of mass of the disk can drop as the disk rolls uphill.
Sample. The three particles in the figure 1, 2, 3 are initially at rest. Each experiences an external force due to bodies outside these three particle system. The direction are indicated. F1, 6.0 Newton, negative direction. F2, 45 degree up, that's 12 Newton. F3, positive direction, 14 Newton. What is the acceleration of the center of mass of the system? And in what direction does it move? These three forces acting on three different particles, we look at they all acting on the center of mass. So we put them together. How do we put them together? We divided each forces into X component, Y component. And the net force X component is the sum of the three components along X. So this is 14, okay? This is -6, and this is 12 cosine positive. And net force along Y is, these two doesn't have any component, only 12 cosine, sine 45. So we combine this together, the net force equal to x squared fy squared square root. Okay, we get the number. And the angle, this angle, we call it tan theta, equal also f net y over f net x, as we learned before. And we found the theta equal to 27. So net force is 18.6, the angle is 35. So the acceleration follow the same direction, that angle 27. And the magnitude is f net over m, is 1.2 meter per second. Linear momentum. The linear momentum of a particle is a vector p, we define as p equal to mv, related to its velocity. Velocity is a vector, so the linear momentum is a velocity. Now let's do some operation. We do the derivative with respect to t on both sides. We know this one. This one is sigma f, right? We can m out. M take it out, we get m dv dt ma. ma equal to sigma f equal to f net. So we get this one, dp dt equal to f. What does this mean? This means the time rate of change of the linear momentum of a particle is equal to the net force acting on the particle and it in the direction of the force. This is fact 2. The linear momentum of a system of a particle, P equal to sigma pi, 1, 2, 3, 4, 5. Then we write it down. And P1 is M1V1, P2 is M2V2, P3 is M3V3 by definition. And this red formula seems familiar with us. In the center of mass, we find out this is equal to total mass multiplied by velocity of center of mass. Okay, so then we get the total linear momentum of the system that equal the total mass times the v corp. Conclusion: the linear momentum of a system of particles is equal to the product of the total mass m and the velocity of the center of mass. This is the one. This is equal to sigma f, sigma external. This is the generalization of the single particle equation to a system of many particles. This is the vector equation. So we write a three-component equation. Sigma net x equal to dt dp px equal to net x. Same thing for y and for z. These equations are independent with each other. Okay. Sample. Figure shows a 2.0 kilogram toy race car before and after taking a turn of a trail. Its speed is 0.50 meter per second before the turn and 0.400 meter per second after turn. What is the change delta P in the linear momentum of the car due to the turn? That's very simple. Okay, we see this is the Pi, so this is minus Pi. This is a P final. It's a matter P final. What the delta P? Okay, the delta P definition is P final minus P initial, or P final plus minus P initial. This is delta P. Okay, now we write this one. V1 is the 0.50J. This is minus because of that. So P1 is MV1. M is 2.0. V final is this positive 0.4 Ji along the x direction. So P final is MV final is I. And then the change delta P equal to PF minus PI. So this one minus this one. That's all. Newton's second law for a system of particles. Sigma F external equal MA com. F equal to MA, but each term have different meaning. One, sigma F external is the vector sum of all external forces that act on the system, not necessarily on the center of mass, on the system, any particle. Forces exerted by one part of the system on another are called internal forces, and you must be careful not to include them when using above equation, because sigma F internal equal to 0. We have explained before. Second, M. M is the total mass of the system. We assume that no mass enter or leave the system as it moves, so that M remains the constant. This system is said to be closed. 3. A com is the acceleration of the center of mass of the system. This equation gives no information about the acceleration of any other point of the system, only center mass. Let's prove it. Well, R center mass equal to sigma MI over M, where M is the sigma MI. We write it down. We move M over here. M R com equal to sigma M1 R1, M2 R2, M3 R2, and Mn Nn. Now, let me do something operation. We do the derivative with respect to time t on both sides, and M is constant, M1, M2 are constant. We take it out. So this formula becomes big M V com dr dt equal to V. This becomes V1, V2, V3, Vn. And furthermore, we do the derivative with respect to time t on both sides in this equation. We take this out. dv dt is acceleration. So this is A com M1, A1, M2, A2, M3 until Mn, An. What are this? This is a sigma F acting on M1. And this sigma F, including two parts, external force, internal force. We put this force together. All these forces, including internal force and external force. And we summarize sigma F external force plus sigma F internal force. As we know, explained before, sigma F internal force of a system is equal to 0. So we get F external sigma equal to ma dot. This is the Newton's second law for a system of particles. In the application of Newton's second law, the system of the particle may be replaced by a single particle located at the center of mass. The mass of this single equivalent particle being the total mass of the system of the particle. Okay. We rewrite this in three components. We get they are independent with each other as before. Okay. Sigma f x equal to m a com x. Sigma net y equal to m a com y. Sigma net z equal to m a com z. They are independent. So this looks like a single particle's Newton's second law. And this single part is center of mass. As we mentioned before, the center of mass of a body or a system of bodies is the point that moves as though all the mass will concentrate there and all external force will apply there. Two O's.
When we place a cylinder on this pair of inclined rails, it rolls down the incline. If we place this double cone on the incline, it rolls up the incline. Why does this object appear to defy gravity? The rails spread apart in the uphill direction. This and the shape of the double cone allows the center of mass of the cone to go lower as it moves up the rails. Here's a shot from the side.
When we place this disc on an incline, it rolls downhill. If we place the same disc on the incline again, it rolls uphill. What could account for this unusual behavior? If we turn the disc around, the reason becomes clear. A heavy weight has been added to the disc near its edge, shifting the center of mass. The center of mass of the disc can drop as the disc rolls uphill.
Sample. The three particles in the figure 1, 2, 3 are initially at rest. Each experiences an external force due to bodies outside these three particle system. The direction are indicated. F1, 6.0 Newton, negative direction. F2, 45 degree up, it's 12 Newton. F3, positive direction, 14 Newton. What is the acceleration of the center of mass of the system? And in what direction does it move? These three forces acting on three different particles, we look at they all acting on the center of mass. So we put them together. How do we put them together? We divided each forces into X component, Y component. And the net force X component is the sum of the three components along X. So this is This is 14, okay? This is minus 6, and this is 12 cosine positive. And net force along y is, these two doesn't have any component, only 12 cosine sine 45. So we combine this together, the net force equal to x squared fy squared square root. Okay, we get the number. And the angle, this angle, we call it tan theta, equal also f net y over f net x, as we learned before. And we found the theta equal to 27. So net force is 18.6, the angle is 35. So the acceleration follow the same direction, that angle 27. And the magnitude is f net over m, is 1.2 meter per second. Linear momentum. The linear momentum of a particle is a vector p, we define as p equal to mv, related to its velocity. Velocity is a vector, so the linear momentum is a velocity. Now let's do some operation. We do the derivative with respect to t on both sides. We know this one. This one is sigma f, right? We can m out. M take it out, we get m dv dt ma. Ma equal to sigma f equal to f net. So we get this one, dp dt equal to f. What does this mean? This means the time rate of change of the linear momentum of a particle is equal to the net force acting on the particle and it in the direction of the force. This is fact 2. The linear momentum of a system of a particle, P equal to sigma pi, 1, 2, 3, 4, 5. Then we write it down. And P1 is M1V1, P2 is M2V2, P3 is M3V3 by definition. And this red formula seems familiar with us. In the center of mass, we find out this equal to total mass multiplied by velocity of center of mass. Okay, so then we get the total linear momentum of the system that equal the total mass times the v corp. Conclusion: the linear momentum of a system of particles is equal to the product of the total mass m and the velocity of the center of mass. This is the one. This is equal to sigma f, sigma external. This is the generalization of the single particle equation to a system of many particles. This is the vector equation, so we write a 3-component equation. Sigma net x equal to dt dp px equal to net x. Same thing for y and for z. These equations are independent with each other. Okay. Sample. Figure shows a 2.0 kilogram toy race car before and after taking a turn of a trail. Its speed is 0.50 meter per second before the turn and 0.400 meter per second after turn. What is the change delta p in the linear momentum of the car due to the turn? That's very simple. Okay, we see this is the pi, so this is minus pi. This is a p final. It's a matter p final. What the delta p? Okay, the delta p definition is p final minus p initial, or p final plus minus p initial. This is delta p. Okay, Now we read this one. V1 is the 0.50J. This is minus because of down. So P1 is MV1. M is 2.0. V final. V final is this positive 0.4 Ji along the x direction. So P final is MV final is I. And then the change delta P equal to PF minus PI. So this one minus this one. That's all. Impulse linear momentum theorem. Collision and impulse. A collision is an isolated event in which two or more bodies, the colliding bodies, exert relatively strong forces on each other for a relatively short time. Two relatively. We must be able to distinguish times that are before, during, and after a collision, as suggested in the figure. In the illustration, a certain boundary surrounded the two colliding bodies. The forces that our bodies exert on each other are internal to the system. Many physicists today spend their time playing what we call the collision game. Our principal goal of this game is to find out as much as possible about the forces that act during the collision, knowing the state of the particles both before and after the collision. Virtually all our knowledge of the subatomic world, electrons, protons, neutrons, muons, quarks, and the like, comes from the experiments involving collisions. The rule of the game are the laws of conservation of momentum and of energy. Single collision. For single one, we have a dp dt equal to F. F is the force acting by this one. Okay. And we move this from dt over, you get a dp integration equal to P equal to F T dt integration. What is this one? This one, we will give a name called it impulse. The integration for this one is from initial states, Pi, this is Ti, to the final states, T final, and P final. Okay. Now we'll give this one called an impulse. The definition of impulse is J equal to this graphs. Ft dt integration from Ti to T final, we call it an impulse. Okay. Mathematically, this is a F curve versus T. This is T. So this integration J is the area of this purple area, right, from mathematics. Okay. And this is very hard to calculate because this is a changes rapidly. So what we do, we think it is an average force multiplied delta T. What is this? This is we find an F average. Okay. So that this area blue color is equal to this area of purple color. Okay, and we can estimate this one. Okay. So from this one we get P final minus Pi equal to delta P equal to J. J is the impulse. Impulse linear momentum theorem. J equal to P final minus P initial. That's a delta P. What is it? It's an integration. Okay. F T dt integrate from Ti to T final. From this vector equation, three component equations, we have three. Okay. Jx equal to P final x minus P initial x equal delta Px, and so on. Jy equal to P final y minus P initial y equal to delta Py, and Jz equal to delta Pz. Okay? These equations are independent with each other. Jz, Pfz never involve this one, delta Py, delta Px. This is delta Pz, and so on. Series of collisions. This is a situation. This is a series projectiles hit the target with velocity v. Okay. Now we'll see this target is fixed. So this means the projectile either drop or rebound. Okay. And for this target we have P final minus P initial equal to minus n delta P. What does this mean? This delta P is the linear momentum change for each projectile. How many? You have n per second, n per unit time. So total together, their change is n delta P. And this target is minus, just opposite, right? Just opposite. So this is target, opposite. Now we'll see that the F average equal to J over delta T. I put a J sign. Okay. This is minus delta P over delta T. Okay. And if you see that P equal to mv, so this is equal to m delta V. Each project are the same with mass m, velocity change mv. And we read by nm is 1 second per unit time. We have n projectile. Each one has mass m. So this is big M called a delta m, delta t. Okay. This is delta v. What is this one? This is a mass change rate, where delta m equal to mn. And when projectiles have two situations, hit and stop down, then delta v equal to v minus v. Okay. If you rebound back with the same speed, so the projectiles rebound with the same speed, then we see delta v equal to minus v minus 2v, double. And the F is double 2.
When an egg is thrown against a wall, the forces which stop it are large and act over a very short period. How could we stop the egg without such large forces so that the egg will not break? If the egg is thrown against a loose sheet, the total change in momentum is the same as before, but the forces acting on the egg are small, and the collision takes more time. The egg remains intact.
This pile driver has a weight that can be dropped to crack a piece of plastic. If we put a piece of foam rubber over the plastic, the amount of energy released in the fall is about the same, but the collision takes place more slowly. The size of the force on the plastic is thus reduced, and the plastic does not crack. This animation shows the forces which act on the weight and the plastic, first without, and then with the foam rubber in place.
Sample. Race car wall collision. Figure is an overhead view taken by a race car driver as his car collides with the racetrack wall. Just before the collision, he is traveling at speed VI 70 meters per second. This one. along a straight line at the 30 degree from the wall. Just after the collision, he's traveling at the speed 50 meters per second along a straight line at 10 degree from the wall. His mass is m 80 kilogram. Question A. What is the impulse J on the driver due to a collision? We know the J equal to delta P. P final is mv final. P initial is mv initial. And we put this one, take m out, equal to m v final minus v initial. Okay. We have this number, so we get a J. Okay. This is vector, so we have to do it on the axis, the scalar case. This is P initial, P final. Okay. So the Jx equal to m v final x minus vix. Okay. We're going to look at this one. This is the final. We've got an x. Okay. So this is equal to, this is m 50 kilo. This is v cosine. This is minus 10 degree. Okay. And this is minus p v initial. This is initial. Okay. Cosine 30 degree. Okay. So you get a vx, jx. Okay. Also, we have to go to jy because we're going to find a j. Okay. The jy equal to m v final y minus v initial cap. Now, v final y is negative. V initial y is upward positive. So we put this 50 sine 10 minus 10. This minus number. And this is 70 sine 30, positive number. Okay. We get the jx and jy. Then we get a j. Okay. The jxi plus jxy. Okay. We can get its magnitude and direction too. Now, this is j. This is x. X is minus number. Y is minus number. So this is j direction. Okay. J, the magnitude equal to jx squared plus jy squared. We put a number inside, we get number. And theta. Theta looks as also y tangent theta. This tangent equal to y to x. We get 50.4. And the total number is this one, plus 180. Okay. Or you can go look at this one. It's 180 minus this one is minus. Okay. So this is 255.4 degree or minus 105 degree. Question B. The collision lasts for 14 milliseconds. What is the magnitude of the average force on the driver in a collision? Now, this is easy because we know, okay, this one equal to J over delta T. We know J, just calculate. Delta T is given, so we get F average, pretty hard, 10 to the 5th Newton, okay, 100 ton. And acceleration is F average over M. It's very hard too, okay, about 300 G. So, conservation of linear momentum. Suppose that the sum of the external forces acting on the system of particles is 0. The system is isolated. And that no particle leave or enter the system. The system is closed. That means isolated system, closed system. Putting F net equal to 0 in above equation. Okay. The dp dt equal to F net. Okay. So this is 0, dp dt is 0, or P is constant. P is a constant. It's called a closed system, isolated system. P is always constant. This is an important result called the law of conservation of linear momentum. Can also be written as P initial equal to P final. where the subscript refer to the value of P at some initial time, I, and some later time, F. If no net external forces acts on a system of particles, the total linear momentum of the system cannot change. Like the law of conservation of energy, the law of conservation of linear momentum is a more general law than Newtonian mechanics itself. It holds in the subatomic realm, where Newton's law failed. It holds for the highest particle speeds, where Einstein's relativity theory prevails. Above equations are vector equations, so that when F net equals to 0, along x direction, Px constant. F net y equals to 0, Py equals constant. F net z equals 0, Pz is constant. Okay? These three components are independent with each other. F net x, nothing to do with Py or Pz. If the component of the net external force on a closed system is 0 along the axis, then the component of the linear momentum of the system along that axis cannot change. This is what, okay?
These two equal mass gliders with spring bumpers are moving on a nearly frictionless air track. If we tie the gliders together with a string, the springs try to push the gliders apart. If the string is burned, the gliders fly apart with equal but opposite velocities. If we now double the mass of one of the gliders and repeat the demonstration, what will the relative velocities of the gliders be after the string is burned? The glider with twice the mass now moves away at half the velocity of the lighter glider.
Sample. A ball box with mass m 6.0 kilogram slides with a speed v 4.0 meter per second across a frictionless floor in the positive direction of an x-axis. It suddenly explodes into two pieces, one piece with mass m1 2.0 kilogram moves in the positive direction of x-axis with speed v1 8.0 meter per second. What is the speed of the second piece with mass m2? We know in this case no external force. P initial equal to mv, one pieces. P final, you have two pieces, okay? Two pieces. m1v1 plus m2p2. Okay. Since they are isolated, no external force, so P final equal to P initial. It means E2. We get mv equal to m1v1 plus m2v2. Okay, now we know m 6.0 kilogram. We know v 4.0 meter per second. We know m1 2.0 kilo. Of course, we know m2 because m minus m1 is m2. Okay, and we know v1. Okay, 8.5. So we can find the v2 principle. Very easy one. Okay, we put number inside. We get v2. v2 is 2.0 meter per second. Sample. A firecracker placed inside a coconut of mass big M, initially at rest on a frictionless floor, blows the coconut into three pieces, A, B, C, that slides across the floor. An overhead view is shown in the figure. Piece C, with mass 0.30 m, has final speed 5.0 meter per second, C. Okay. Question A. What is the speed of piece B with mass 0.20 big M? Now we look at this one. A, B, C. Okay. We know the situation C, mass. Now this B is 0.20 M. Of course, we know BC, we know mass A too, right? So we choose axis so that P final A, Y is 0. It along the x direction. This is x direction. Okay. Now totally we know it's a rest, so P initial equals 0. And then finally what? Finally, these 3 plus along is 0. Okay. If I equal to 0, that means if I x equal to 0, if I y equal to 0, component equal to 0. And F final you have 3 pieces, okay? It should be equal if I equal to 0. This is a conservation, linear momentum conservation. Okay. Now with this condition, we can find P final x, okay, equal to P final y equal to 0. This is a general situation. Okay. Now we get to pieces A, B, C. Based on the conservation of linear momentum, PFY equal to PIY equal to 0, right? And PFY, the final state, you have 3 pieces. P final AY, P final BY, P final CY. Okay, AY is 0 because we choose the reference. Let's see this one. BY, that is B. B along this way is B sine 50 minus. Okay, it's a minus number. Go direction. The C is positive direction. Okay, equal to 0.3 m sine 80 degree along this one. Okay, this Y. The 3 put together should be 0. And then we can find V, B, V final B, okay, because V final C is given, okay, so we can V final B. Question B, what is the speed of piece A? This is final, okay, this is final. We have piece C, piece B, so that's very easy to find the piece A, because piece A along x direction is only along x direction, okay, but 3 put together equal to 0, original, okay, original. And then we know that both speed of VC and VB, okay. So this one equal to the final AX equal to the speed, the mass 0.50 m minus V final A. This is this one. I don't know. That's what we want to find. Okay, on A. And we have this one and this one we can calculate. Okay, the final BX equal to mass 0.24 VB cosine 50. This one, F final CX, C along X equal to mass 0.30 mass. VC, this one is cosine 80 degree. And we put these 3 into this equation, okay, we get VA, 3.0 millimeter. Momentum and kinetic energy in collision. The discussion will be limited to collisions in systems that are closed, no mass enters or leaves them, and isolated, no net external force act on the bodies within the system. We see the kinetic energy of the system kinetic energy is conserved. It is same before and after the collision in an elastic collision. Or this is called kinetic energy is conserved. Okay, and kinetic energy is not conserved. Okay, in an inelastic collision. So you have two different categories: energy conserved or not. But the linear conservation is always conserved. Kinetic energy of the system can conserve or not conserve. Okay, kinetic energy is conserved. It is the same before and after the collision in an elastic collision. Reverse, in an elastic collision, energy conserved. Energy conserved is not conserved in an inelastic collision. Linear momentum. In a closed, isolated system containing a collision, the linear momentum of each colliding body may change, but the total linear momentum P of the system cannot change whether the collision is elastic or inelastic. This is the law of conservation of linear momentum. Also, no external force involved. Collision. Inelastic collision in one dimension. An inelastic collision is one in which the kinetic energy of the system of gliding bodies is not conserved. One-dimensional collision is one-dimensional. V1, I, M1, M2, V2, I, initial, okay? And then they hit together. After that, they move this direction. Why is this direction? We assume. If we get the number is negative number, that means its real motion is going back, okay? Anyway, we assume all move forward, okay? And in this case, beside these two methods, nothing else happened. So we see F net is equal to 0. In other words, the linear momentum P of this system is constant. P1I plus P2I initial equal to P1 final plus P2 final state. Okay, this is a linear momentum that always conserved, whether energy is conserved or not. We write this one. This is a M1 V1 initial plus M2 V2 initial equal M1 V1 final plus M2 V2 final. That's one equation. The kinetic energy that is lost in any inelastic collision is transferred to some other form of energy, perhaps thermal energy, sound energy, deformation energy. Nonetheless, the linear momentum of the system is always conserved, provided the system is isolated and closed. Since kinetic energy and the linear momentum both involve the speeds of the colliding bodies, so the conservation of linear momentum limits just how much kinetic energy is lost by a system in an inelastic collision. Complete inelastic collision. We have a complete. What does it mean? It means these two collide and they becomes a what? Okay. After clashing, the bodies stick together. Okay. So this is they move together. Okay. We assume V2 initial is 0. Okay. Then we see the linear momentum conserved M1 V1I, the linear momentum before collision is equal to they move together m1 plus m2 v. So the v equal to m1 over m1 plus m2 v1 initial. This is the velocity of center of core. After or before, okay? After, before, always that's this one. Okay. When the bodies stick together in a completely inelastic collision, the amount of kinetic energy that is lost is the maximum allowed by the conservation of linear momentum. So the conservation of linear momentum limited the energy lost. Velocity of center of mass. Look, this is a particle 1, particle 2. This is the center of mass. You see, the speed of center of mass is always constant because it's isolated system. Okay, F external is 0. Linear momentum conserved. Okay, so we know the P is m v com equal to m1 plus m1 v com. This one is also m1 p1 initial plus p2 initial, right? Yeah. So the vcom equal to p over, this is the vcom is p over m1 plus m2, and this p is equal to p1 initial plus p2 initial. That's the vcom. Okay, this is what. Always constant, okay, unaffected by the collisions. This is before collision, after collision, they are the same velocity.
This demonstration uses gliders floating on an air track to show two different types of collisions. In the first collision, two identical gliders have spring bumpers which can return to their original shape after being squeezed. When the gliders collide, they exchange velocities. If we turn the gliders around, they will stick together after they collide. After the collision, how will the velocity of the combined gliders compare with that of the first glider? The two gliders together move at half the velocity of the original glider.
This device, called a ballistic pendulum, can be used to measure the speed of a flying ball. A spring gun on the base fires a steel ball horizontally. In order to determine the speed of the ball, we'll catch it in the bottom of this pendulum arm. The height of the rise of the center of mass can be used to calculate the original speed of the ball. Here are some sample firings of the ball, first with the spring compressed this far. Then with the spring compressed more. And with the spring compressed even more.
Sample. The ballistic pendulum was used to measure the speeds of bullets before electronic timing devices were developed. The version shown in the figure consists of a large block of wood of mass 5.4 kilogram, hanging from two long cords. A bullet of mass 9.5 gram is fired into the block, coming quickly to rest. The bullet then swing upwards. The center of mass rising a vertical distance h 6.3 centimeter before the pendulum comes momentarily to rest at the end of the arc. What is the speed of the bullet just prior to the collision? Okay, that's just prior to the collision. Now, we think this one much easier. Mechanical energy conserved. Before is half mv squared. After they have the high is m plus m, that goes high h together. So they should equal. So very easily, we know h, we can find v. It is right. In this process, mechanical energy conserved or not? We know that one. After what it hit, you will hear the sun. You have sun energy. You will feel the blood was heated. Okay, you have a heat energy disappear, right? Yeah. So apparently, mechanical energy in this case does not conserve. Then what we do is, whatever it is, linear momentum is conserved because this two system external force is zero, right? So the linear momentum conserved. Before, the linear momentum is mv. After they move together is m plus mv. This is a linear momentum curve. In this process, kinetic energy or energy is not conserved, mechanical energy, okay, because you have a heat energy disappear, right? And then after that, these move together. During that goes no other heat, no other energy. So we have energy, mechanical energy conserved. Here you have velocity together, they move half mv's equal to the big mgh. This is a very important process. In this process, the mechanical energy does not move. After they move together, the mechanical energy conserved again. Okay? With these two equation helps, we very easily find the v. Okay, we find the v. Okay, it's very simple calculus. I'm not going to do it. Okay, we put the number inside. Okay, inside. Okay, and very easy to find v equal to 630 meters per second. Elastic collision in one dimension. If the kinetic energy of the system is the same before and after the collision is then said to be of a special type called elastic collisions. In an elastic collision, the kinetic energy of each colliding body may change, but the total kinetic energy of the system does not change. In a closed, isolated system, the linear momentum of each colliding body may change, but the net linear momentum does not change, regardless whether the collision is elastic or not. Look at the stationary target. The second target is stationary, V2 initial 0, and V1 is approached with V1 initial, final, initial. Now, after hit, we still assume this one move forward. It can move back, okay, but we assume it is move forward. Then we write the equation. If we find the answer is a negative number, that means the real motion is going back, okay? So linear momentum, see that before the collision is m1 v1i. This is 0. And linear momentum conserved because this is isolated, okay, closed system. So equal to linear momentum after collision. After collision is m1 v1 final plus m2 v2 final. Okay. And we have energy conserved. Before collision is half m1 v1i squared equal to, after that both have kinetic energy, half m1 v1 final square plus half m2 v2 final square. These two equations, we can find the v1 final and the v2 final. It's very easy. Now, we move this one over, okay, and half will cancel out. m1, this is m1, we m1 take out. m1 v1i square minus V1 final square will become V1I minus V1 final multiplied by V1I plus V1 final. And this is M2 V2 final. And look at this one. Okay, look at this one. We move this one over because M1 V1 minus V1 final equal to M2 final. And we look at this is the same. This is a part of the same. So we divide each other, we find out, okay, V1I plus V1 final equal to M2 this equation. Okay? So this equation plus this, or linear, it's very easy. Look at the two equations. Look at this, the speed of center of mass is always constant, okay, before collision and after collision. That's the answer we get. Now let's see this one. Equal mass, M1 unit. After collision, this is 0. This is a 2M1, 2M1. So V2 final equal to V1I. What does this mean? This we call it, if mass is equal, they exchange speed. V1 final is 0. Actually, it's V2 initial. It's still. V2 final equal to V1 in the exchange, right? So this is 0. Okay, this is 2. They exchange it. A massive target, M2 is much larger. M2 is much larger. I can drop this one and drop this one. This is okay, minus plus minus. So V1 final equal to minus V1 initial. What does this mean? It goes back with the same speed. Okay? It goes back with the same speed. And the second one, the massive target almost move a little bit because this M2 is much larger than 2. It's very small. The third condition is the massive projectile. M1 is much larger than M2. In this case, we drop this one, M1 over M1. M1 final equal to M1 initial. That means it does not move, it just continue move. We can match, right? Yeah. And you know the second one, M1 is much larger than 2. This drops. This becomes 2. So M2F is leave very fast, double speed. For motion of the center of mass, this is P equal to M com. Okay. So this is a constant. This is a constant. So V com is a constant. Okay, it's constant. It's always constant.
These sets of pendulum balls will be used to demonstrate collisions between various masses. Here is a pair of equal mass balls. When we collide one ball with the other, the two balls trade velocities. The incoming ball stops, and the stationary ball flies away at the same speed as the incoming ball. Here's a set of balls with a 3-to-1 mass ratio. When the small ball strikes the larger one, the small ball bounces back and the large ball moves away slowly. What will happen if the last collision is reversed? Now, the small ball flies away quickly, and the large ball continues in the same direction at a lower speed. Here is a set of balls with an 80-to-1 mass ratio. When the small ball strikes the larger, it bounces back completely, while the larger ball hardly moves. Here's what happens when the last collision is reversed. Finally, here is a set of 11 pool balls hung in a row. When we pull back and release one ball, a single ball flies out the other end. If we release a larger number of balls together, the same number flies out the other end.
We will illustrate different types of collisions using gliders floating on a cushion of air. These two gliders have the same mass. They exchange velocities upon collision. What will happen if the stationary glider is heavier than the moving glider? In this case, the lighter glider moves backward after the collision. The heavier glider moves off at a lower velocity than the initial velocity of the lighter glider. What will happen if we switch the gliders so that the heavier glider collides with the lighter stationary glider? This time, the moving glider continues on the same direction after the collision, and the stationary glider flies off at a higher velocity. Now we will try it with the stationary glider of a greater mass.
Moving target. Both moving, okay? And we have energy conserved. Half m1 v1 initial square plus half m2 v2 initial square equal to half m1 v1 final square plus half m2 v2 final square. Energy conserved. And then linear momentum conserved. m1 v1i plus m1 m2 v2i initial linear momentum equal to final linear momentum m1 v1 final plus m1 m2 v2 final. This is a one-dimensional, so it's not fact, just kind of scale. So let's solve this two equation. We can get v2 v1 final and v2 final. How we do that? Now we look at this one. We changed equation because minus. This is m1 m1, this is m2 m2. Okay. Same thing, this is m1 m1, this is m2 m2. We take this out, okay. So half cancel out. This is m1 v1 final square minus v1 initial square minus v1 final square, a square minus b square equal to a minus b multiplied by a plus b. The same thing happened on the right. This is a square minus b square equal to a minus b plus a plus b. Okay. This one, we move it, take it m1 out. This will be m1 v1 initial minus v1 final minus m2 v2 times c. Now, we look at this equation. It's different. Now, they are the same. They are the same. So we divide it. On the left, one turn left, one final plus one final equal to this minus cancel out 1 2i plus 1 2 final. So this equation, okay, plus this equation, two linear, very simple equation, we can find v1 final and v2 final easily. Okay, now these two very easy. Okay. Now we get this answer. Yeah. I don't remember this one because we can very easily get this answer. Okay, now
When two balls with the proper mass ratio are dropped together with the lighter ball on top, a very interesting bounce occurs. The heavy ball barely bounces at all, but the lighter ball bounces many times higher than the drop height.
Now this is the answer. Notice that the assignment of subscripts A1 and 2 to the body is arbitrary. If we exchange those subscripts, we end up with the same set of equations. Okay. This is this one, there's symmetry. Sample. two metal spheres suspended by vertical cords initially just touch as shooters would initially. Okay. With M1 30 gram is pulled to left to hide H1 8.0 centimeter and then released. Okay. After swinging down, it undergoes an elastic collision with sphere 2, whose mass is 75 grams. What is the velocity V1 final of the sphere 1 just after the collision? I want to find this one. That's an easy one. Okay. Now, which is energy conservation. The velocity from here, so the potential energy change M1 at GH1 equal to half M1 initial square. We can find the speed from here. Okay? They put a number inside, we get 1.252 meter per square. Now, with this one, we use the formula. This is the one we want to find one final. Okay? We final. This one, initial 0. So V2 initial 0. So this is the formula. Okay? We put the number inside. We get a number. Okay? We get a very easy one. Okay? This is minus. What does this mean? What this means is it bounces back. Bounce back. Collisions in 2 dimensions. This is 2 dimensions, not head-on, so split into 2 directions. Okay. Glancing collision, not head-on. V1I, V1 initial hit this one equal to V1 along the x direction, I, and the target is 0. V2I is 0. After the hit, they split the 2 directions. So we have linear momentum conserved both in x direction and y direction. So we split into 2. Elastic collision, you have energy conservation. Okay, so K1I plus K2I equal to K1 final plus K2 final. Okay, now we do this one. M1 V1I, this is 0, this is 0, equal to M1 V1 final plus, this is this direction, cosine theta 1 plus V2 final, cosine theta 2 is along x direction. And along y direction originally is 0. And you have, this is M1 V1 final, sine theta 1. Plus, this is M2 V2 final cosine theta 2. Okay? Now plus the elastic energy conservation. Initial energy plus 2 kinetic energy. Okay? We have 3 equations, but we have a lot of variables. Okay? There's 7 variables. Okay? You see V1 initial, V1 final, V2 final. Okay, V1 initial 0, okay, M1, M2, theta 1, theta 2, altogether you have 7 variables. We have 3 equations. We need 4 given condition can solve this question.
We'll demonstrate 2-dimensional collisions using these Airtable pucks. The pucks have equal mass. We'll have them collide in different ways and watch how they move after the collision. Here is a head-on collision. Lines on the screen will follow both pucks to make their paths visible. This is a collision where the puck strikes slightly off-center. This time the puck strikes even farther off-center. Notice that after an off-center collision, the pucks move off at approximately 90 degrees to each other.
We'll use this Airtable to demonstrate inelastic collisions between pucks floating on an Airtable. The pucks have Velcro strips around the edge to make them stick together. We'll have them collide in various ways and then watch them after the collision. This pair of pucks has equal mass and collides slightly off-center. This is the same pair of pucks colliding farther off-center.
We'll demonstrate two-dimensional collisions between unequal masses using these pucks floating on an air table. This pair of pucks has a mass ratio of 2 to 1. We'll have them collide in various ways and watch how they move after the collision. Here is a head-on collision. Lines on the screen will follow both pucks to show their paths. Here is a collision slightly off-center. We'll now repeat the two last collisions with the heavier puck running into the lighter puck.
Sample. Two skaters collide and embrace in a completely inelastic collision. Thus, they stick together after impact, as suggested by the figure, where the orange is the place at the point of collision. Alfred, whose mass M8 is 83 kilograms, this is 8, is originally moving east with speed VA 6.2 kilometers per hour this direction. Barbara, whose mass MB is 55 kilograms, is originally moved north with speed VB 7.8 kilograms per hour. Question 8. What is the velocity V of the couple after they collide? That's very simple. Now, we see this, okay, is the direction, okay. Y direction. Before the collision is MBVB. After collision is big M V sine theta. And this direction, before the collision is MAVA, okay, and after the collision, MV cosine theta. We'll find the theta first, okay. We divide this two, okay, we get a tangent theta, they cancel out, equal to MBVB of MAVA, so we get 0.834, we get theta. Is about 40 degrees. Okay. Now we find the velocity. The velocity is MBVB over M sine theta. We put the theta inside, we get a number, okay, about 4.9 kilometers per hour. Question B. What is the velocity V of the center of mass of the two skaters before and after the collision? We know the center of mass velocity is the same. We know after the collision they move together. This speed is actually the speed of center of mass before and after the collision. That's it. Okay. Sample. Two particles of equal masses have an elastic collision. The target particle B initially addressed show that unless the collision is head-on, the two particles will always move off perpendicular to each other after the collision. Now, they move off. This angle is perpendicular, 90 degrees. Phi is 90 degrees. Prove it. Now let's see this one. M1 equal to M2 to M. So we have linear momentum cancel. Okay. The first one is M1 V1I. The second one is 0. Is at rest, stationary. And after collision, you have MV V1 final plus M V2 final. This is the equation. Also, mechanical energy conserved. Okay. Half M V1I initial equal to half M V1 final square plus half M V2 final square. all right? And this equation, we cancel m, cancel half m. We get a two equation. V1I equal to V1 final plus V2 final. V1I squared equal to V1 final squared plus V2 final. Now let's see what's happening. We square both sides. This becomes V1I squared. This becomes V1 final square plus 2V1 dot V2 final plus V2 squared. And we compare these two equations. This is equal to the term, this is equal to the term, so this term must be 0. 2 vector itself is not equal to 0. Dot equal to 0 means cosine theta equals 0. Theta is 90 degrees. They're perpendicular. Systems with varying mass, a rocket. The system is a rocket. We eject our combustion product. So this system has two parts. And this is a closed system, okay, an isolated system. Okay. So the total mass does not change. The system is closed and isolated system. So the linear momentum conserved. Before ejected and after eject, the linear momentum of the system is constant, equal. That's the physics. Now we start it from this one. We eject combustion stuff called delta M. After ejected the product, the mass left in the rocket is m minus dm, with speed increase v plus dv. And the velocity of this rejected product in the Earth's frame, or in the sun frame, which is we call inertial frame, is u. So before it ejected, the limited momentum pi of the system is mv. And after ejected, you have two parts. One is this one, mass is m minus mi. The velocity is v plus dv, plus the ejected product, mass dm, velocity is u. This u is the velocity, the projected product to the ground. And we don't know that one. We know the relative speed, Vp rocket, okay? So we use the formula, we split into two, Pg, and then put R inside. What this means? This means the velocity of prepared products in the ground is equal to the velocity of the prepared product for in the rocket plus the velocity of rocket in the ground. And this one is relative speed of the prepared products and the rocket. We call it V relative. And this is the velocity of rocket in the ground, which is V plus dV. So U equal to V relative plus V plus dV. We put back in this equation, and we make Pi equal to P final. So this is Pi, this is P final. The P final is M minus dm, V plus dV, dmu. U we replace by V relative plus V plus du. And we do the calculation. mv, mdv, minus dmv, minus dmdv, plus V relative dm, dmv, dmdv. Okay, so look at this one. mv cancel out. Okay, dmdv minus cancel out. Okay, and minus dmv plus dmv cancel out. So we only have two turn left. Yes, get it. Minus dmv relative equals mdv. This is the physics. So let me write it down. From this equation, we can find the acceleration of the rocket. How will you do that? We write this down. What is the acceleration? Acceleration is dv dt. So we divide the equation on both sides by dt. This is acceleration. Okay. And what is this? This is dm dt minus. Dm dt is the mass loss of the rocket in this period. We call it R. Okay. So this minus R relative speed equal to ma. We know ma equal to the force. Okay. So here R is dm dt. What is it? The rate at which the rocket loses mass. Okay. So this equation, ma is the force. We call it thrust force. Okay. T. When you eject these products, you get thrust force ma. And then from this equation, we can find the velocity of the rocket. This is dv, the change of the rocket. So we do the integration. We move the m over there. So we get the dv equal to minus v relative dm over dm. We do the integration on this side to dv. This side is the m. So we get v final minus v initial equal to relative log m and minus. And we put the limit between it up. So this initial, this is the final. Have already called the minus sign. So this we call the second rocket equation, find the velocity. This is the first rocket equation, we find acceleration and force.
We'll make this rotation stand spin using the force provided by a small cylinder filled with carbon dioxide. When the back of the cylinder is punctured with a pin, the carbon dioxide jets out of the cylinder, and the stand rotates in the opposite direction as the escaping gas. This animation shows the pressure acting on the inside of the carbon dioxide cylinder before and after it is punctured.
Here is a toy water rocket. We're going to fire the rocket first with water exhaust, then with air only, and show the difference in the rocket's acceleration. We'll first fill the rocket half full of water, then pump the handle 10 times to raise the pressure in the rocket. When the rocket is launched, the water exhaust boosts it very high. If we leave the water out and fill the rocket with air only, how high will it go? We'll pump the rocket twice as many times to make the pressure in the rocket the same as the last time. Here goes. The rocket hardly moves at all.
The spray from a carbon dioxide fire extinguisher looks a lot like the exhaust of a rocket. And like a real rocket exhaust, the escaping CO2 can accelerate a large mass. We'll use this extinguisher mounted on a rolling wagon to accelerate a person to suborbital speed. 3, 2, 1, blast off! Engine cut off.
Chapter 9, Rotation. Welcome you make a comment and give suggestions so that this program can be more helpful. Acknowledgement. This video clip is a part of my lectures on college physics during 1990 to 2021, based on the adapted textbook Principles of Physics by Holliday, Resnick, and Walker, published by Wiley. The demo videos were bought from a company in USA by my university for teaching. They helped a lot. I'm sorry for not remembering its name to show my appreciation. It seems that they came from the University of California, Santa Barbara, where I got my PhD in physics. Thanks God.